today we want to model the Ctran W problem. So first click on new, click on add, and CW steady state, and no change on the definition stuff, the key in analysis. Close it, and we will start. First we have to save. So first we are for the Ctran W we have to model the CW part and then Ctran W, because we want to find the flow of water inside the soil first and then the contamination flow in the soil. So first we will start with the CW. The first part is the geometry, so we have to define the points first, and then when we inserted all of the points like this in the key in points, we have to define the geometry. So 0 0 0 175, and the rest of the points, as you can see, we have to insert the points. This geometry is the same for all groups, so you can use this geometry, and based on the group numbers and the table, you can find H1, H2, X value, and the soil type, which are not the part of the geometry. So we can define the geometry by these points that I just inserting in here. So first, as I said, we have to define these points to define the geometry, and for CW and the Ctran W we have the same geometry. So if you see, we have just one point in here, because this, if you click like zoom out, you can see we have how much points. So we have to increase the scale of the sheet to make all of these points part of that page that we are working for. So for horizontal we are changing it to 10,000, and for vertical we will change it to 1,000. So we increase the maximum value of the X and Y, and we are changing the units as well. You can see all the points in this page. Now we have to define the geometry. So point by point we are linking the points to each other. We are connecting to the points to each other, and like this. If you click around the points, then the software itself click on the points. So that's all. We define the geometry, and now we have to define the material. Second step. So this step we will change the name to ground soil, and we have to define the water function, water content function. Changes to for my soil, which is a sand water function. So we are going to estimate and click the saturated water content for my soil, which is sand is 0.65, and I will use a sample material sand, and that's all. I have the curve for that. The next important part is water content function. We have to change the none to sand water content. For the other function, we have to define the hardware conductivity function, same as the previous one. We'll do this the same, like water content function, and the K value we have to find it from the literature. So based on the literature and this table, we can see defined sand hydraulic conductivity is 10 minus 5 to minus 10 minus 3. So 10 minus 2 would be the good estimation for this, which is the centimeter per second. So the unit that we have in the software is meter per days, so we have to change this number based on the unit. So 8.64 for based on the new unit that we have, meter per days. So we'll change this to 8.65. For the residual water content, 0.3, there we can see the curve also, and that's all. We have to change none to water, sand, hydraulic conductivity, and close. So we have to save and to draw, click on draw materials and click on the region, and that's all. We have defined the material, we allocated the material. But now if I want to save, you can see this is the Ctran edition, and we cannot have more than 500 elements, so we have to increase the element sizes for the Ctran license. So we are going to draw mesh properties and increase the 15 meter to 25, so you can see the elements numbers decrease to 472, which is lower than 500, and that's fine. We can do this in the student license. Yeah, so we save it again, and the last part we did boundary condition for CW. So as a default we have the seepage phase. We have to define the other boundary condition, which is the oil sand tailing pond. In this part, yeah, we are changing the color, and you can change it or not. And the action, which is 163 meter, I will explain it why I changed it to this number. And for the other Bosca river, we have to define the other boundary, which is 115 meter, and close. So why we are using these actions for the oily sand pond? You can see the vertical distance from the surface of the oily sand pond to the base of the soil is 163 meter, and for the river this distance is 115. So that's why we have the total head equal to 163 for the tailing pond and 415 for the river. The next step, we have to define the point at the middle of the line to make this line, separate this line to two lines, and allocate the boundary condition to for the river and for the tailing pond. Same as the tailing pond, we have to define the point at the middle of the line for the river side to make the line into two parts, and define and allocate the boundary condition. So click on the draw boundary condition and change to oily sand. Click on the middle of the line, and we will have the boundary condition for the oily sand and river. And for the rest of the line, you can see the potential seepage phase. So same as the previous one, if you click on save, you have the same problem for the elements. You can change this element size again to something else to reduce the element numbers. So if you change it to 25 again, you'll have 477 elements, which is fine. Click on save, go to key in to add the Ctran W analysis to our analysis. So additive dispersivity, adversive dispersivity. So we have to change the seepage results to parent analysis to use the CW results in here. But the time, we have to increase the time to 730 days, and you can change the steps because this contamination has been exist from 2 past years, so we have to use 730 days or 2 years for our analysis. We have to define the material for the Ctran W. So all of these properties belongs to the contamination in the soil. So for the longitudinal dispersivity, we have to define the distance between the middle of the tailing pond to the middle of the river, which is the horizontal distance is equal to 1550 minus 300, something around 1250. and so if you multiply this amount to 0.1, then there would be the good estimation for the longitudinal dispersivity. So 125 is equal to that parameter in the definition of the material properties, 125. And for transversal dispersivity, you have to define the vertical distance between tailing pond and the river. This vertical distance is on our region is equal to 50 meters. So if we multiply this amount to 0.1, then we have the good estimation for the transversal dispersivity, which is 5 meters, and click 5. And we have to define the adsorption function as well. So we are clicking on we can change the name to toluene and the type. So click on add. We have two points for my adsorption function. I found this from the literature for the sand and the toluene. It was 2 points on this curve, and then I inserted those points, and then I have the line. I have to change the adsorption function to toluene and the dry density to the amount for the sand, amount of dry bulk density for the sand. So that's fine. We define the geometry, we define the material, and we have allocated the material as well. We have to define the boundary condition now. So click on boundary condition, and we're defining the oily sand tailing pond, tailing pollution pond, and then we have to change the action to 1 gram per cubic meter. It is for my example, based on your group number, you have to find the value of x and insert that for the action of the tailing pond pollution. We have the other boundary, which is the free exit boundary, which is the mass flux. It has to be 0 gram per days, and that's all. So we define the boundary condition. We have to allocate this boundary condition to the region. So click on draw boundary condition. For oily sand pond, just click on the middle of each line for the tailing pond, and for the free boundary condition on the surface of the soil, we want to find. We have to insert the boundary condition on the free exit boundary. So we have verified, we solve the CFW first, and it takes some time to solve it. And yes, we solved the CFW part and the Ctran W both. 20 steps to pass, perfect. So we define, we solve it, and for the CFW part, you can see the analysis results. So we have the water level on tailing pond and the river, and we have the equipotential lines as well. For the Ctran W, you can see the results like this. So the contamination released to the soil and polluted the soil by different levels. If you comes to this, you can see how was the contamination. We can increase the levels to increment by 0.1 and increase the number of the colors to